Hello and welcome. My name is Yanoa and I'm a PhD student at the Low Gravity Science and Technology Lab at Georgia Tech. Today I will present you the presentation I gave at the beginning of this year at the AIAA SciTech 2026 forum on equilibrium and stability of orbiting liquid mirror telescopes. Starting out with the motivation and the question what liquid mirror telescopes, or LMTs in short, even are. The concept of LMTs dates back to the 1850s, with Newton providing the key observation with the rotating bucket experiment. You can see that on the right side as an illustration, and I'm sure you've seen that before in person too. If we're rotating a bucket or a liquid containment of some sort, a paraboloidal surface forms, and that is actually the perfect shape for a mirror. So if we're spinning a liquid metal or some highly reflective liquid, we can use that as a mirror. And that's a very or relatively low cost method for creating optically smooth reflective surfaces. However, it also has some disadvantages. One of the disadvantages is that it's inherently limited to points zenithwise due to the way that the interface is formed by the gravitational and the rotational potentials. And it also requires a relatively high accuracy in the rotational control to form the optically smooth interface. On the bottom left, you can see the image of the largest LMT so far, and it's the 6-meter large Zenith telescope, which was built in the early 2000s but decommissioned about 10 years ago now. Now, why should we bring LMTs to space? Advantages of LMTs in space are low body force potential, which could mean that we would either need only low interface control requirements, or might even get away with no interface control. So we wouldn't need to spin the dish, for example. And that would allow us to easier tilt and just use it basically just like a regular telescope in the best case scenario. Additional advantages could be the in-space assembly of the mirror. Just by injecting a liquid, the interface forms and we would have the mirror. Other disadvantages would be self-healing. So after a micrometeoroid hits the mirror, the fluid moves back into that place and forms the interface again. On the right side, you can see an illustration of a current development in orbital LMTs, which is the NASA Fluidic Telescope, or FLUTE in short, and it's developed by a team at NASA Ames in collaboration with Technion. Since this is the only development in space-based LMTs so far, we're using that as a baseline for all the computations that we're doing later. A key question that remains, however, is if it's possible to have purely passive capillary-driven LMTs, so without any interface control. The goal of this study is to assess the interface response of orbiting liquid mirror telescopes to environmental perturbations that we're facing in the orbital environment. In step 1, we want to identify and describe the orbital perturbations mathematically. Then afterwards, we are creating a model, which in our case is axisymmetric. And in step 3, we're determining the optical compliance of the interface. Before we can start with step 1, we need to look at the governing equations for interfaces in low gravity. And those are, on the one hand, the Navier-Stokes equations in combination with the Laplacian boundary condition at the interface. We're taking the following simplifications. Since it's a fluid, or a liquid rather, it's incompressible, and we're looking at the equilibrium, so at the steady state. Therefore, derivatives of time are 0 and the velocity in the fluid is 0. With these simplifications, we arrive at the governing equation on the bottom left, with the pressure in the medium being 0, since we're in vacuum. The symbol pi notates the mass force potential, so the combination of all the different perturbations. Speaking of perturbations, the first source in our environment is solar radiation pressure, which is nothing else than the force from the sunlight caused by the momentum transfer of photons onto the spacecraft. Since liquid mirror telescopes are very prone to environmental effects and, to be honest, pretty much everything, depending on how strong the control is, You also need to control the temperature very well, since most properties of liquids depend on temperature, like surface tension, density, etc. And therefore you would need some type of temperature control, which would definitely involve a sun shield, and that would be the interaction with the solar radiation pressure, and thus that governs the interaction between SRP, solar radiation pressure, and the spacecraft. The general equation can be seen on the left, but due to the interaction with the solar sail, or not the solar sail, the sun shield, we can take some simplifications. And we're also assuming that the beta, which is the vector between the sun line, so the direction of the photons, and the normal of the sun shield is approximately 0, since we want to direct our sun shield to be perpendicular to the sun to shield the telescope. With these simplifications, we arrive at the expression on the right side. The next perturbation is self-gravitation, which is the gravitational pull on the one hand from the fluid particles onto the other fluid particles, but also from the rest of the structure and of the service bus. We're approximating the structure itself as a point mass and using a point mass potential for that. But for the mirror, we're using an expression which is used for like celestial bodies, or bodies in space, which are axisymmetric, and we have that long expression to determine the self-gravitation potential with that. The process of that is pretty complicated, since we're iteratively changing or adapting the self-gravitation potential to what we're projecting the interface to be, but more on that can be read in the paper itself. The last effect that is dominant in our environment are the tidal effects, which are caused by the difference in gravitational pull between the near and the far side of an object in space, and it results in a stretching and contraction. I'm sure you've all heard about tides, which are caused by the moon, and tidal effects due to it. Difficulties of tidal effects for our model are, on the one hand, that tidal effects are expressed in the orbital frame, so it depends on the alignment between the orbital frame and the frame that we're working in, the telescope frame. And since we don't want to look at all the different possible orientations, we're just looking at the best and the worst case. Best case means, in this case, the least interface deformations to the baseline spherical, and worst, the largest ones. Moreover, tidal effects are very non-axisymmetric in nature. Since we still want to employ a axisymmetric model, we're doing a best case approximation. So we're looking at deformations that are actually lower than what you would face with those tidal effects, and underestimating the interface response. We're doing that by assuming that the forces would be radial, since, for example, if you look at a rubber band and you're stretching it only in one direction, like the tidal effects would do, you would see very large deformations, compared to if you apply that force radially. Since it's kind of counteracting each other, you would just see smaller deformations. Coming to our model, we are employing a arc parameter parameterization for our interface, which is technically not needed, but if you have loops in your interface, that would be what you would do, and we wanted to use that in future projects. Then we're also adding a volume conservation and the following boundary conditions. We have 3 boundary conditions for the axis symmetry of the interface. We have 2 boundary conditions for the volume conservation, and we have another one for the interface spinning. Now, interface spinning is the interaction of the interface at the wall. We don't want the interface to slide, having a constant contact angle, and instead we want it to be pinned, allowing for different, I don't want to call them contact angles, since the contact angle is the same, but interface angles to the wall, basically. In step 4, and the final step, we need to solve the boundary value problem that we created. And for that, we're using the shooting method, in which we are not imposing two of the boundary conditions, but trying to iteratively match those. So we're iteratively integrating the ODE, starting from the center of the interface, and we will keep going until we hit a certain maximum value in S, our arc parameter, and we will do that until we match those boundary conditions that we didn't impose. And as you can see on the bottom right, you can see kind of how the algorithm works. We get closer and closer to the actual interface. Coming to our findings, and we will start out with the non-dimensional analysis. Here you can see all the different perturbations that we looked at and the corresponding bond numbers. What is pretty clear is that, especially for tidal accelerations in GEO, the bond number quickly gets very, very large and on the order of a few thousands. So we are not further looking into that orbit, since in terms of purely capillary-driven LMTs, it's just not feasible at all. Moreover, we see that Galinstan, so the liquid metal, exhibits slightly lower bond numbers throughout, which means, at least in that regime, it's slightly favorable. We also see that we don't really see the interface response in this. So there's no way to judge if it's still if the optical performance is still good enough for us. So we need to look at the interface response, which is what we did in the next step. Here you can see the interface response for a 30-meter Galinstan-based LMT. This is just for the general shape of the perturbations, since as you can see, the magnitude of those, or the magnitude of the interface deformation due to the perturbation, is very large. Our interface depth, so the film thickness, is 1 centimeter, and those deformations are at the order of centimeters to even almost 10 centimeters in the case of the tidal forces in GEO. Yeah, so the only small one that we can't even notice here, the deformations, are the tidal forces in SEL2. The others are pretty large for larger apertures. So the question that remains is, how large can capillary-driven LMTs become while still satisfying optical quality? What does optical quality or optical compliance mean? We have the following requirement. In optical or in telescopes, you generally want to have a maximum wavefront error of lambda 10. And if we translate that to a maximum surface error or optical path difference, that translates to about lambda 20th. So we ran the simulation for varying apertures for all the perturbations that we face in SEL2, Sun-Earth L2, and we came up with the following relation between the shortest observable wavelength and the aperture of the Galinstan-based liquid mirror. And if we extract some values out of that, we can see that for IR observation, so lambda is 10 to the minus 4, we get a maximum diameter for observing that of about 2.9 meters. And for visible light, it's only 0.64 meters. So while this doesn't show us the exact numbers, since there were some simplifications that went into the model, it shows us that at least for larger apertures, you definitely need some type of interface control to use them for observations. What interface control mechanism could be used for that? Now, on the one hand, we could use electromagnetic actuation, which means we could use passive or actively controlled magnetic fields and some type of magnetic liquid that we manipulate with those. For Earth-based LMTs, there's actually development going on in that direction, and that is through the DARPA Zenith program, which our group is also working on an implementation for a tiltable terrestrial LMT, which could easily be transferred to space. Thermocapillary effects are another mechanism that could be used, and that makes use of the temperature dependence of surface tension. And by that we can, or due to that, we can impose a temperature gradient, and that will lead to a reposition of the fluid, so internal flows within the film. The conclusion of my study is that purely capillary-driven LMTs are highly susceptible to present perturbations in our orbital environment, and thus the optically usable size limitation is on the order of a few meters, depending on the observed wavelength. And we also need interface control for larger apertures. In the future, an assessment of the interface control mechanisms should be done, where it's assessed what type of interface control mechanism would be viable and what you would need in terms of accuracy, etc. Additionally, the dynamic response should be looked at, since that is the relevant part for the potential benefits that I named, so for self-healing and the in-space assembly, to see how quick those happen. Thank you for your attention. If you want to read the full paper, it can be found at the QR code. And yeah, contact me if you have any questions. Thank you.